So now let's take a look at an activity that can make use of these derived tables as well as common table expressions. Here we're going to be making use of the SQL3 books database, and in particular we're going to be taking a look at the book table as well as the order item table. So here for this activity we want to answer the following questions. First, what is the top 5 most expensive books? In our particular database, we know that can be answered by taking a look at the book table, right? So we select from that particular table and we just choose certain columns such as ISBN, title, and retail. So select ISBN, title, and retail from book. And then we want to get the top 5 most expensive books. So the way we can do that, we just order the book table by retail price and descending order so that we get the most expensive books first and then the least expensive books last. And then we just limit the result set by 5 so that we can get the top 5 rows with the most expensive retail prices. So as you can see here, Painless Child Reading, Holy Grail of the Oracle, and other books are the top 5 most expensive books. Second, let's say we wanted to identify the top 5 most ordered books. That particular information can be found in the order item table. And in this table again, right, it specifies how many orders have a certain book have been secured. So here, for us to be able to identify those, we have to select the ISBN, and we're actually going to be using that ISBN as a group statement because there are several instances of the ISBN in the table itself. So let's group by our table by the ISBN, and then we take the sum of the quantity and we just rename it as quantity. From order item, then we group it by the ISBN so that we can aggregate up the quantity values, and then we order by quantity, descending order similar to the previous query, and then we limit by 5 so that we can get the top 5 most ordered books in this particular database. So if we run this piece of code, we should see the following result set. Now, to answer the question, what books are both in top 5 most expensive and top 5 most ordered books, we will need to essentially make an inner join between the top 5 most expensive books as well as the top 5 most ordered books, right? In that particular situation, we can either make use of a derived table or a common table expression so that we can calculate beforehand the top 5 most expensive books, then the top 5 most ordered books, and then we can use those subqueries to answer our last query, which is which books are in both of those groupings, right? So here we create 2 CTEs. Here we just define one CTE called P5P, short for top 5 by price. And that particular query, or rather that particular CTE, is calculated by the first query that we made use of before, right? To get the top 5 most expensive books. Then we define another CTE, which we call top 5Q, which is short for top 5 by quantity. And the query for that particular common table expression is the code that we used to answer our second question, which is what is the top 5 most ordered books. After this, we can then create a statement where we select the columns that we need, and then we can inner join our top 5 most expensive books and then our top 5 most ordered books, right? So here in our last statement, we just select the ISBN, the title, the retail, and the quantity of the books from T5P, right? The top 5 most expensive books, inner joined with the top 5 most ordered books on T5P.ISBN equals T5Q.ISBN. And if we execute this piece of code, we'll know that Painless Child Rearing and database implementations are both part of the top 5 most expensive books as well as the top 5 most ordered books. All right. Here we have another example of making use of a common table expression to answer the following questions. what is the average price of books by category from top 20 most expensive books, right? So in these kinds of compound questions, always better to take a look first. What do we need to calculate first or to transform first before we can answer the question overall, right? So we notice here we need first to get and identify the top 20 most expensive books. Afterwards, we can then calculate the average price of books by category, right? So that's what we did accordingly in our query. We first created a subquery in the form of a common table expression, which calculates the top 20 books by price. And the calculation is as follows. Select ISBN, title, category, and retail from book, and then we order it by retail, descending order, and then we limit by 20 so that we can get the top 20 most expensive books. Afterwards, we can then select the following columns. So category and the average of retail as average retail. And we want to group by essentially our top 20 books by category. So that's why we're getting all of the books from the CTE of T20P, and then we're grouping it by category. If we execute this piece of code, we will get the following results. So the average price for the top 20 books in this particular database by category is as follows. The family life books by average are the most expensive when you consider the top 20 most expensive books, and so on. Right. Now let's move on to another discussion point, which is about views. So essentially, when we want to be able to store a query that we often make use of in your querying, you might want to store them as a view, right? So views essentially are virtual tables, but don't confuse views as a copy of an existing table, right? In actuality, views are stored queries. They only store the query that we've defined, but they don't actually create copies of the rows of data or the columns of data, right? So it's more akin to a function in Python. When we define a function, right, we don't necessarily create data already. We are just defining the steps that we want to apply. And the same applies for views, right? We are storing the steps that we want to apply to certain other tables in our database. And then, yeah, we can call that view, right? Similar to how we can call a function in Python. We can call that view or invoke that view in order to execute the query and for furthermore to produce the result set that we want. Okay, so when we create views, it's best if we create views for intermediary transformations or queries that we often use or are repetitively used in your activities, right? So if they're not used often, it is not recommended to actually make use of a view, right? A CTE or a DT can work fine. But again, if you often use a particular query to retrieve data, it might be best to just define it as a view. And the syntax for creating a view is as follows. Create view, view name, as select C1, C2 from table. So it's very similar to creating a table in SQL. However, the difference here is instead of providing column names for creating a table, instead we're providing a query. All right. So here, we go back again to our previous exercise where we wanted to calculate the total prices from all books, from all authors. We can use that query and we can save it as a view called v. So that's what we did here. Our subquery, we store it as a view called v, so that when we use another select statement later on, we can just invoke that view and use it as a source table. So select average v from total price as average price from v will return us the same result from before. All right, now let's move on to our discussion about window functions. So a window function in SQL is an aggregate-like operation that is applied to a result set. So it is aggregate-like in the sense that you can apply aggregations like sum or average or whatnot. But the main difference is that when you make use of a window function, it does not necessarily collapse the rows into a single result. Often we may make use of aggregations, right, like sum or min or max. The result set will be often be collapsed to a certain number of rows, right? So if let's say you just took the average of the prices of the entire book table, right? The result set will be just one row, right? Which collapses all of the prices of the books and just returns one row essentially. But sometimes you don't want to do that. Sometimes you don't want to collapse your rows. Instead, you'd want to use that calculation of that aggregation and make it present for every other row in the result set. So, yep, we can make use of a window function for this particular approach. Okay, so for this particular discussion, let's just take a look at an example of what these window functions are. First, we'll make it very simple. Let's take a look at this one partition window function. So the structure of a select query with a window function is as follows. It's very similar to what we've seen before. We select columns and we can also do an aggregation. So select C1 and the aggregation of C2. We directly put in this keyword called over directly after that aggregation column so that we can essentially specify the partitioning of this particular row. Okay. Right now, you'll notice that this over statement is empty. And what that'll do is it will treat the entire table as just a regular, rather, it will not try to look into the table as multiple partitions. It is just one partition. And partitions are a bit difficult to explain without any illustration. So actually, before I proceed to discussing multiple partitions, let's try to look at it in practice. So here we have a window function. We want to be able to first we're just selecting the author name, the title, and the price from the book column, or rather the book table. And if we do that, we execute this piece of code, you will get the following results. We have author name, title, as well as the price columns, and we have several rows of data representing these, right? So let's say we wanted to get the sum of all of these prices, right? Usually what you would do, you would apply a sum aggregation to the price, right? But from before, it'll just collapse it into one singular row. So instead of just providing the sum of the price, right, as an aggregation, we will actually make use of this over statement so that this particular aggregation is no longer just an aggregation function, it is now a window function. And as you'll see here, what the window function does is it will apply that aggregation, right, the sum, but it will essentially return that sum as another column, and it will apply to all rows in the result set. So if you take the sum of all of the prices in this result set, the window function will return that sum and distribute it to all of the rows that are present. Okay, so you'll notice here there is an additional column here called sum price over, and what it does is it returns all of the rows of data without having to collapse the entire result set, right? So we just return this particular situation. It's actually demonstrated on code.